Greetings, everybody. Hello, and welcome back to another Math 104 lecture. So today what we're going to be looking at is if you're following along in the textbook, the chapter that we're on is now chapter 3.2. So in the last lecture was 3.1. And in this lecture, we're going to be looking at polynomial functions. So polynomial functions, what is a polynomial? If you guys have forgotten, a polynomial is always going to be in the form that I've just underlined, which is some coefficient and multiplied against x, so our variable, raised to some exponent, plus a different coefficient, plus, x to the next highest exponent. So if our highest exponent was a 4, the next highest would be 3, so on and so forth. We write this in descending order of exponents. And obviously, when we get down to the last two, we use, a sub 1 to recognize, again, it's a different kind of coefficient, and x to the first power, which you could just write as x. I put the 1 there just to, keep everything matching, but it's really just x. And then our final number here, a sub 0, well, that's just a constant, right? We're used to seeing constants by now. We've already actually seen plenty of examples of polynomial functions, even if you don't immediately realize it. Quadratics are examples of polynomial functions. A quadratic function, which is, and one more time we're going to write it, ax squared plus bx plus c. Well, this quadratic function or quadratic equation is very much a polynomial. It's just a polynomial whose highest power is 2. The reason that we write to the nth power for polynomials is because anything that, regardless of how high the exponent goes, as long as it follows this form, then it is in fact a polynomial. So the exponent could be 77, and as long as it's, descending from, x to the 77th power, moving on from there, then yeah, it's absolutely a polynomial function. So there are 3 main properties of a polynomial function that we should go over. Oh, and I'm sorry, one other example of a polynomial function which we should all be familiar with at this point, on top of quadratics, is linear functions, right? With our highest power being x to the first power, which should make sense here, right? If you got rid of everything in front of the piece that I circled, well, that's just a linear function, right? You have some coefficient times x to the first power and a constant. So linear function, we should all be familiar with that. So that's just 2 examples of the polynomial functions that we've dealt with already, but obviously the exponents can go much higher than just 2. So we're going to kind of look at that a little bit today and see exactly what's going on. But anyway, so for properties of polynomial functions, there are 3 that we have to concern ourselves with. So the first, and probably the most relevant and the most important to us when we're looking at functions and to verify that something actually is a polynomial function, is its domain. So obviously it has to be in this form as underlined, but also on top of that, the domain has to be all real numbers. So another way of thinking about that is the domain is always going to be from negative infinity to positive infinity. There's not going to be a single number that is going to be outside of the domain. Now, when we talk about things like the square root of, x, for example, a reason that we know that that's not a polynomial function is because the domain is not all real numbers. So we start to see a pattern here when we work with the polynomial functions. It'll start to make a little bit more sense. But the first thing that you should always keep in mind is domain. It's all possible real numbers. Okay, so the second thing is that the graph, when you're looking at the graph of any polynomial function, it's going to be continuous. There's not going to be any holes or gaps in the graph. And what do I mean by that? I'll show you in just a second when we talk about the third point as well. But just keep in mind, it is continuous. There's not going to be a single break in the graph. And lastly, again, in regards to the graph, there's not going to be any sharp corners. It's only going to be consisted of smooth curves. When you think of a parabola, there's really no point in a parabola, which is this U shape. There's no point in this U shape where there's any sharp corners. There's nothing that's, just kind of hits a point and then bounces right back, right? It curves, even though there's a vertex here. It curves through the vertex. It's very smooth, right? That's just something that you should keep in the back of your head while we're looking at these polynomial functions and while we examine some functions that really aren't polynomial functions. And one way to tell is by looking at the graph. So let's look at two examples of functions. They are functions, but we'll look at examples where they're not going to check off, the second and third item of our properties. So one graph that we can look at is the graph of the absolute value of x. So the absolute value of x goes something like that, right? So it bounces off in two different directions. And okay, well, where is this, how do we know that this is not a polynomial function? Well, the reason that we know this is this breaks rule number 3, right? Notice how right here, which I've just circled, actually we'll circle it in red just so it's more apparent. So right at that specific location, notice that there's a sharp corner. It's hitting the origin and it's bouncing straight off the origin going into a different direction, right? The entire idea is that that's not going to happen with a polynomial function. Polynomial function, again, is going to just curve through a point, but not bounce off of it. Okay, and another example of a graph, which once again will be a function. So give me one moment to draw it. So let's say we had something like this. And we've already seen something like this before. This, in general, we call this a step function. And I'll just draw one more here. And we'll say that goes on to infinity. So now notice that this passes the vertical line test, right? And we talked about this before. The reason that we know it passes the vertical line test is that although it hits 2 points, only one of the points is included in our domain, right? All the open circles are not included in our domain. So you don't have to worry about one input giving multiple outputs. That's not going to be an issue for us here. So as a result, yeah, this is absolutely a function, but this breaks rule number 2. Rule number 2 says it has to be continuous. Continuous, again, means no holes, no gaps in the graph. And we can see very plainly, and I'll start drawing them in red here, there's a gap here, there's a gap here, there's a gap here, right? And it's not continuous. It doesn't flow like all the time from one point to the next. So that's how you know that this is also not a polynomial function. Okay, so those are your 3 properties of polynomial functions, 2 of them regarding graph and 1 of them regarding the domain. Okay, so let's go ahead and clear this off and let's talk about the first definition that you should be aware of. So the first definition you should be aware of is called a power function. So a power function is the very simplest bare bone version of a polynomial function. It's always going to be in the form of f of x is equal to a times x to the n, and I'll write down here a is not equal to 0. Okay, so a can't be equal to 0 because if a is 0, then it doesn't matter what x is or whatever your exponent is either, because then you'd obviously just get a 0 function. So that wouldn't make much sense. So your coefficient can't be 0 here, but this is, again, what's known as a power function, and I'm abbreviating function. Okay, so we've actually, again, if you think about quadratics, we've already seen an example of a power function. It was just a really basic example. When we talked about a quadratic like this, yeah, this is absolutely a power function, right? It looks like it could be in this form. Our a, in this case, is a 1, and our n, our exponent, is a 2. Sure. This is absolutely a power function, but just keep in mind that your exponent is not always going to be 2 and your coefficient is not always going to be 1. You might get, for example, something like this, 4/7 times x to the 4th. And this is, once again, another example of a power function. The reason that we call this the simplest of polynomial functions is because there's only the one term. Now, you, in general, when we're talking about polynomial functions, you're probably going to start seeing things like, like x to the 3rd plus, yada, 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 right? And it goes in descending order, and there's going to be a bunch of terms that get added or subtracted here. But in a power function, you don't have that. A power function is simply just the one term and its leading coefficient, okay? So it's coefficient here, which again, in this case is 4/7. Okay, so there's something very cool or very interesting about power functions in particular, and it's that power functions are symmetric about the y-axis if the highest power is even, and they are symmetric about the origin if the highest power is odd. What do I mean by this? Okay, let's look at the super basic example that I just drew before. F of x is equal to x squared. And we already talked about how, yes, this is absolutely a power function, and yeah, we'll put a 1 in there, just to really solidify that we know that our coefficient here is 1. What is the graph of this going to look like? Well, we should all be pretty familiar with what parabolas look like at this point. We know that it's going to be symmetric about the y-axis, right? Well, this is actually the case not just for 2, but for 4, for 6, for so on and so forth. As long as you have a power function, so as long as you just have the one term, and as long as your exponent is even, it's going to be symmetric about the y-axis. So your line of symmetry, your axis of symmetry, is going to be the y-axis itself. Okay? Now, the other thing that can happen is if you have an odd exponent. So now we're going to look at x cubed, which we've kind of dealt with before, but maybe you forgot what this looks like. So as a brief refresher, what this looks like is it looks kind of something like this. So it's kind of like you took half of your parabola and pointed it downwards instead. So this, believe it or not, is in fact symmetric about the origin. And how do you know that something is symmetric about the origin? Well, we actually talked about symmetry going back several lectures ago, but symmetry is where, you plug in the negative versions of y and the negative versions of x, and you should still end up with the same answer, right? So if we're talking about f of x is equal to x cubed here, and we know that f of x is the same thing as y, so we're just going to put in y in here. We know that something is symmetric about the origin when we plug in the negative versions of both y and x, and we end up with the same equation. So let's go ahead and test that real quick. Let's plug in for y, we're now going to have a negative y, and for x, we're now going to have negative x cubed. Well, negative y, there's no simplification to be done, right? It's just going to be negative y, and negative x cubed. Well, when you cube a negative, or when you cube any sign for that matter, it's always going to remain that sign, right? When you square something or when you raise something to an even power, it's always going to be positive. When you raise something to an odd power, it retains whatever sign it has. So because we're taking a negative x, our output is still going to be negative. And then we just have x cubed, right? But what can we do here? If we have a negative y is equal to negative x cubed, we know that we can just cancel the negatives, right? We multiply both sides by -1 or divide both sides by -1, however you want to consider it. And we still end up with y is equal to x cubed, right? So notice we get the same thing by plugging in the negative versions of y and x as we do by just having the original equation. And that was our test going back to see if something was symmetric about the origin. And to see graphically what that looks like, that's as if you drew this line here, which kind of cuts through the origin, and it should be symmetric about that line, which, I freehanded this, but it's fairly symmetric about that line. And if you don't believe me, feel free to plug it into a graphing calculator and it'll give you a better picture than I can draw. Okay, so point is that whenever you have an odd function and it's a power function, so when I say odd function, I'm talking specifically about the exponent. Whenever you have an odd exponent for a power function, it's going to be symmetric about the origin. And when you have an even exponent of a power function, it's going to be symmetric about the y-axis. Okay? Okay, let's go ahead and erase this. So now we have to talk about polynomial function end behavior. What is end behavior? Okay, so all polynomials, regardless what the exponent, regardless what the polynomial, will always tend, so graphically, it will always tend to the leading or the highest power term. Remember, we write it in terms of highest power first, and so that's why we call it the leading term, the highest power term. So all polynomials will tend to the leading highest power term. So let's take, for example, f of x is equal to 4x to the fourth minus 8x cubed plus 2x squared minus 7. Now we can see this is a fairly complicated polynomial, right? And I'm not going to ask you guys to find the solutions to this or the x-intercepts. We don't have to worry about that. All I want to prove here is that the leading term, which in this case is 4x to the fourth, is going to be the most important term. And the reason that this is the most important term is, remember what I just said, that the polynomial will tend to the highest power term. What that means is that as x, so as your input gets larger and larger and larger, it gets very, very, very big, right? And it goes off to infinity, all of the other terms, except for the leading term, matter less and less and less. So what do I mean by that? Okay, well, if we plug in x is equal to 1, we see that there's going to be a big variation here, right? Like when we plug in x is equal to 1, x to the fourth, x to the cubed, and x squared all return the same thing, right? X to the fourth, when you plug 1 in, gives you 1. Same thing with x cubed and x squared, right? So x cubed and x squared play a really big part when x is really, really, really small. So but we're talking about when x gets very, very large. So, okay, what happens if we plug in 100 instead of 1? Well, plugging in 100, and I'm not going to ask you guys to do this, but I can just tell you, plugging in 100 for x, well, if x is 100, then x to the fourth is, and I'm just going to abbreviate this, 100 million. And again, feel free to plug this into a graphing calculator or any calculator if you don't believe me, but x to the fourth becomes 100 million. X to the third, however, only grows to be 1 million. And x squared, well, x squared is just 100 times 100, which is only 10,000, just a measly 10,000. Now you start to notice here, oh yeah, 10,000 really pales in comparison to 100 million, and 1 million is, although it's at least in the same ballpark, it's significantly smaller than if you just plugged in 1, right? When we plugged in 1, x to the fourth, x cubed, and x squared were all on the same level, right? They all returned 1 back to you. But as x gets larger, the exponent gets bigger or the exponent plays a bigger and bigger part in the output being larger and larger, right? So we see that x to the fourth plays the largest part when x gets really, really big. Now, another way that we can demonstrate this, so if that's still not clear, another way that we can show it is, okay, well, let's just factor out x to the fourth from every single term. Okay, so we're going to take x to the fourth from every single piece here. So that means I'm going to pull out x to the fourth. When I take x to the fourth out from the first term, we're just going to have 4 left, right? We took x to the fourth out from x to the fourth, so we just have the coefficient remaining. Now we're going to have minus 8 over. Now, we started with x to the third. We're trying to take out x to the fourth. Now realize we're taking out 1 more x than we actually have. So we're really dividing by x here, right? There's still that 1x left over that we're taking out. So we have 4 minus 8 over x. Similarly, not a comma, sorry. Similarly, we're going to have plus 2 over x squared. Remember, we started with the x squared. We're trying to factor out x to the fourth. So we're left with still dividing by x squared. And that 7, that negative 7, well, that didn't have any x's. So when we factored out x to the fourth, yeah, it's just being divided by x to the fourth. Why did we do this? What was the point of factoring out x to the fourth? Well, the point of factoring this out is what I want you to do is I want you to realize what happens when x gets really, 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 really big. So start off in your head with, and let's just consider just this term. We're not even going to talk about the other terms just yet. Let's just talk about 8 over x. What happens if x is 10? Well, if x is 10, so if x equals 10, then 8 over x gives you 0.8, right? Because then you would have 8 divided by 10, that gives you 0.8, okay? If x is 100, then 8 over x is going to give you 0.08. Notice that it already got substantially smaller, right? Like it was pretty close to 1, and now it's way closer to 0 than it is to 1. And we can keep going, right? If when x becomes 1,000, then 8 over x gives you 0.008. right? Now we're getting really close to 0. So what do I mean by this? What I mean is that as x grows larger and larger, every single one of these fractions goes to 0. Now, there's a fancy term for this, and if you go and take pre-calc after this course, or you go on to take calculus, you're going to see it a lot there. The term is called a limit. We're not going to really discuss that here. Just know that that's essentially what we're talking about. We're talking about the limit as x goes to infinity. Again, don't worry about the terminology. I just want you to prepare yourself that if you go on to take future math courses, this is what the idea of limit is all about. We're talking about what happens when we, try to plug in infinity for x. So as x gets really big, we see that every single one of these goes to 0. So let me just erase this work real quick. What this tells us then is that as x grows really large, I'm just going to put an approximate symbol. F of x is approximately x to the fourth times 4 minus 0 plus 0 minus 0, right? Every single one of these fractions tends to 0 as x gets very large. So we just have this 4. And then when we distribute that x to the fourth back, again, f of x is approximately just 4x to the fourth. So what was the whole point of this demonstration? The whole point of this is to show you that we may have started with this really, annoying looking polynomial, but when we're talking about the leading term is always the highest power, the x to the highest exponent, and the leading coefficient of that is always just going to be the number that is, multiplied against it, the coefficient of that. So in this case, our leading term is 4x to the fourth, and our leading coefficient is just the 4, right? And the reason that I'm demonstrating all of this to show you what it approximately tends to is because I want to show you that notice how all the other terms drop out, and as x gets very large, f of x is approximately just the highest term. Essentially, all the other terms drop out and only the highest term tends to matter. Okay? And this is a little bit easier to see if you talk about linear equations, right? If you're talking about linear equations, just say, for example, I had f of x is equal to, I don't know, x minus 2, right? When you're talking about just a linear equation, this becomes super easy to think about because if you plug in a small number for x, this minus 2 plays a big part, right? If you plug in 5, then 5 minus 2 gives you 3, and 3 is, decently far away from 5. But as x gets really big, like say you plug in 10,000, well, 10,000 minus 2 is 9,998, and that's still pretty darn close to 10,000. So notice how it's approximately, as x gets very large, it's approximately just x, which in this case is your leading term. Okay, so that is polynomial function and behavior. It's, it might not seem that intuitive, but essentially all that I'm getting at here is that the highest power, the leading term, is the most important for any polynomial. Okay. Okay, so here's something that you guys should definitely be aware of. All polynomials are going to tend to one of 4 cases. Okay, so we're talking about end behavior here. So end behavior, again, means when we're talking about when x gets very big. So all polynomials, regardless what their exponent is only going to tend to one of 4 different cases. And the 4 different cases are as follows. If n is, sorry, indigestion. Oh, God, it's killing me today. If n is even, it'll tend to, and I'm just going to abbreviate here. It's going to tend to either x squared or negative x squared. Okay, so what I'm saying here is that, and again, when we're talking about end behavior, we're talking about the pieces that go off to infinity or negative infinity, right? So like when we're talking about a parabola, I'm not talking about what's going on in here. I'm talking about these pieces, right? The pieces that go off to infinity. So when we're talking about something that has a higher exponent, so let's say some weird stuff is going on in the middle, I don't know exactly what's going on. I don't know the function, but notice how I'm not talking about any of this garbage. I'm just specifically talking about the end behavior, the parts that are going off to either infinity or negative infinity. So in this example, again, this here is x squared, and I don't know what this function is, but I can tell you that this has an even power. And the reason it has an even power is because notice how both of the legs that are going off to infinity, the parts circled in green here, notice how those are, following the same thing that's happening to the x squared, right? They're both going off to positive infinity. So that's what we mean when we say it'll tend to either x squared or negative x squared. And negative x squared, when we're talking about this piece in particular, that is just depending on the sign of the coefficient, right? So we talked about before when we were talking about parabolas, how in the last lecture, how your a, your leading coefficient, determines whether or not the parabola opens upwards or downwards. So if a was negative, if we had a negative x squared, your parabola opens downwards, right? And see, notice how the pieces that we care about that are going off to infinity are both pointing downwards. So if we had something, say, just for example, if we had negative x to the fourth, well, negative x to the fourth, again, don't exactly know what's going on in the middle, but I can tell you guaranteed 100% that its two end legs here are going off to negative infinity. They're just always going downwards. And the reason that I know that is because this is an even power. So it's going to resemble, the end behavior is going to resemble that of a parabola. And because it's negative, I know that it's going downwards. I know that it's opening downwards. Okay? So with that being said, those were the first two cases. And the second two cases, if you understand that, then this part should be fairly easy as well. So if n is odd, so if your exponent is odd, then it'll tend to either x cubed or negative x cubed. And remember, we just graphed x cubed, right? X cubed is this graph right here where you have essentially one leg going off to positive infinity and one leg going off to negative infinity. So if we had, for example, x to the, 77, for example, right? So this is x cubed. And I have no idea what's going on in this area. Couldn't tell you, no idea. But what I can tell you, just off of the fact that I know that this is odd and it is a positive x to the 77th, I can tell you for fact that the end behavior is you're going to have the piece on the right going to positive infinity, and you're going to have the piece on the left tending to negative infinity. Okay? So again, I can't tell you what's going on in that red circle area. That part of the function is a mystery to me because obviously I don't know the rest of the function. And even if I did, who knows what x to the 77th is really going to be, right? Without a graphing calculator. It's going to be, a substantial amount of work. But I can at the very least tell you that the range of this is all real numbers. And I know that because when we're talking about range, we're talking about reading from the bottom value of the y-axis to the top value of the y-axis, right? Well, in this case, the bottom value of the y-axis, notice that this piece goes downward forever, so negative infinity. And this piece goes upwards forever, so positive infinity. So I can tell you, without knowing anything else about the function, that as long as x to the 77th is positive and that that is my leading term here, that is my highest power, I can tell you for a fact that the range of this function is going to be from negative infinity to positive infinity. And again, to a lesser extent, I can guarantee you that the green pieces are going to match the green pieces of x cubed. Okay, and now the last case is if you have negative x cubed. So negative x cubed, it's going to look obviously very similar. The only difference is instead of you having that arrow, what you're going to have is this arrow. So it's going to go that way. And the other piece is now going to go down that way. Okay, so negative x cubed is going to graph like this. And again, I have no idea what this is going to look like. but let's say we have x to the 53rd, and I know that it's a negative x to the 53rd. I can't tell you at all what is going on, close to the origin. I can't tell you what's going on at the center, but what I can guarantee you is that the end pieces are going to match the negative x cubed. So I can guarantee you that these two pieces are going to tend off again to positive infinity and negative infinity. Okay, so hopefully that makes some amount of sense. It's really hard to, to see it your first time around. If this requires more explanation, if a lot of you guys don't understand this, I have no problem going over this in class with actually better, more detailed examples. But I feel like that the best way to learn this is kind of just giving you general examples, like again, x to the 53rd here, what even is that? And that way you can at least see that that number really doesn't matter. What matters is that it's odd and that the negative matches the negative, right? And so if you have a negative sign, you know that the right hand piece is going to be pointed downwards. If it's not negative, you know the right hand piece is going to be pointing upwards. And that's really all there is to it. Okay, so let's talk about solutions of a polynomial function. So much like zeros for a quadratic or solutions for a quadratic, solutions of a polynomial function implies where there is an x-intercept for that function. Okay, so let's look at an example here. Let's say we have f of x is equal to 2x cubed minus 3x squared plus 4x minus 6. And I say to you, I want you to find all the real solutions of this function. Okay, well, essentially what that's asking you to do is find where all of the x-intercepts are for this function, right? This is saying set it equal to 0 and then solve for x. So, okay, that's really not so bad because one of the first things that we learned is if there are 4 terms, try to group it. If we can group it, then we can try to pull something out. And if the pieces match, then, we're in luck. So what I'm going to do is I'm going to say, okay, well, let's go ahead and group this. So by grouping, I'm going to put these two pieces together and these two pieces together. So when I'm talking about the first set of parentheses, the biggest thing that I can take out is an x squared, right? I can take out an x squared, and that'll leave me with 2x minus 3. Okay, this is what we're hoping to get when we try to factor the other parentheses, right? If we can get 2x minus 3 again, just as a refresher for grouping, then we can do that distributive property in reverse, and we can pull out the 2x minus 3 from both of the pieces. So we look at 4x minus 6, and we ask ourselves, what is the biggest thing that we can take out? The largest thing that we can take out is a 2. So we take out a 2, and that leaves us with 2x minus 3. Hooray, right? Our pieces match 2x minus 3, 2x minus 3. So as a result, yeah, we can go ahead and do the distributive property in reverse. We pull out 2x minus 3, and what is left over? X squared plus 2. And we know how to solve this, right? We have two factors, zero product property. We set each factor equal to 0, and we see what we get, right? So we have 2x minus 3 is equal to 0, and x squared plus 2 is equal to 0. Okay, so for the left-hand side, we add 3 to both sides. 2x is equal to 3. X is equal to 3 halves when we divide by 2. So what this tells you is that x is equal to 3 halves. Well, 3 halves on the x-axis is going to be an x-intercept, right? This is a solution for x that's going to, make this true when we, have the left side equal to 0, and left side equal to 0 tells you y is equal to 0. And once again, if y is 0, then this is an intercept. This is an x-intercept. So, okay, we now have gotten one solution. Now we have this x squared plus 2 piece. Okay, what are we going to do with this? Well, you can try a couple different things. You can try quadratic formula. You can try completing the square maybe. Either way, what you're going to get is no solutions, right? And the reason that you're going to get no solutions is because you have x squared, which is only going to return to you a 0 or a positive number, regardless what you plug in for x, right? If you plug in a negative number, it's going to return to you a positive number. And the lowest x squared could ever get is if you plug 0 in. Right? So when we plug 0 in, you know, and again, that's the lowest it'll ever be. You're still adding 2 to it. So the lowest that the left-hand side is ever going to get is 2. And is 2 equal to 0? No, right? So intuitively, you already know that this is not going to work out, but we can try to solve it. So trying to solve it, let's move the 2 over. Let's not mess around with the quadratic formula. It's going to take too much effort to prove the same idea here. So moving the 2 over, we have x squared is equal to -2. To solve for x, we take the square root of both sides. We get x is equal to plus or minus square root of -2. Oh no, we have the square root of a negative number. And once again, this should be a sign for you. No solutions, right? There are technically solutions in the complex world when we're talking about imaginary numbers, but for the purpose of real numbers and for the purpose of x-intercepts, there are no solutions. What this tells you, if you were just to graph x squared plus 2, well, x squared plus 2 is going to be a parabola, and it's going to be 2 units up, right? The 2 tells you that you're moving 2 units upwards on the y-axis. So we know that we're going to be looking at something like this. That was a horrible sketch. My apologies, but it should still get my point across that the parabola is never hitting the x-axis, right? So as a result, yeah, it should make sense that you're going to get no solutions for this factor. And so our only x-intercept, the only real solution of our function up above here is x is equal to 3/2. So nothing too different from things that we already know. Or again, everything that we've talked about before regarding linear, regarding quadratics, all of that stuff applies, you know, same truth for polynomial functions, except polynomial functions, we just don't necessarily have all the tools yet to solve all of the zeros. In this case, we did, right? We had all the tools necessary, and we just found out that there was only one real solution. We're going to see later on in this lecture video an example where I'm just going to give you guys the factors because we just don't have the tools necessary to factor things like x to the 4th just yet. Okay? But point is, we have one real solution, and that's all there is for f of x. Okay, so something else that you should be aware of. A polynomial function of degree n, so we don't know what n is, but of degree n, has at most n real solutions. Now that should make a lot of sense given what I've been telling you guys all along, right? When we're talking about, let's say, for example, we had f of x is equal to x plus 1. Well, this is a linear function, right? It's linear. We know that our highest power is 1. And what does that tell you? That tells you that at most, there is one real solution to this function. If we had, we'll name it something else. If we have g of x is equal to x squared plus, I don't know, 5x plus 6, sure, why not? This tells you your highest degree, so again, polynomial function of degree n, in this case, n is 2. So your highest power is 2. This implies that you have at most 2 real solutions. It doesn't guarantee that you have 2 real solutions, but it does tell you that you have at most 2 real solutions. So if I tell you that, you know, if I give you h of x is equal to x to the, I don't know, let's just do something wild, 101 plus 7x minus 2, right? If I gave you this function, even if you have no idea what this looks like, although given that this is positive and given that this is odd, you can definitely tell me what the end behavior is, right? Again, just short little quiz, right? End behavior is of this. It's odd, it's positive. You know it's going to resemble positive x cubed, right? So just real quick, the end behavior, you know, I don't know what's going to go on the inside, but I do know the end behavior is going to look something like that. But anyway, neither here nor there. That's not what I'm getting at here. What I am getting at, though, is that, again, I have no idea how, what the solutions are to this function, but I can guarantee you that this has at most 101 real solutions. There cannot be 102 solutions for this function because our highest power is 101. Okay? Are we all good with that? I hope so. If you have any questions, please let me know. Okay. So let's move on to something where we're finally going to get to your first classwork problem in just a second. Okay, let me just clear my canvas. Okay, Now we're going to talk about something called the Intermediate Value Theorem. This is one of the first, other than the Pythagorean theorem, this is one of the first theorems that I want you to know by name. Okay, so Intermediate Value Theorem, also known as IVT. Okay, so IVT. And I'm going to write this all out, so bear with me for 1 second because I do want to write it out. It's going to look like just a bunch of jargon, and then once I write it out, it'll make a lot more sense, or once we do an example. So let's let A and B be two numbers. And I'm just going to talk over this and not correct my handwriting, so please, just make sure you have your volume up because there's no guarantee you're going to be able to read this. Let A and B be two numbers such that, which I'm also going to abbreviate as ST, such that A is less than B. If polynomial function f has f of A and also f of B with opposite signs, then there is at least one point C where A is less than C is less than B, for which f of C is equal to 0. Once again, that looks horrible. I imagine that as you were reading this or as you were listening to me write this, you were probably just dozing off or scratching your head going, what does this even mean? This is really intimidating, but it is super simple once we actually get into it. Okay? What I want you to do is I want you to imagine, let me just draw a little picture, right? So let's say this is a road, right? So here we go. Here's a road. Here is you, right? Okay, so you're right here. And there is a pizza place, which please do not make fun of my diagram. Okay, I'm going to do the best that I can here. So pizza, right? Here's a pizza place. And that was not supposed to be a roof. That was supposed to be a pizza slice. But you know what? So be it. Okay, so here's a pizza place, right? Okay, so here's the question I have for you. Is there any way for you to go from where you are to the pizza place without crossing the road? And for the purpose of this hypothetical, assume, no jetpacks, no teleportation, no airplanes, right? Just from where you currently are, is there any way for you to cross this boundary, cross the road without hitting the road, without crossing the road? Is there any way for you to do that? And again, just assume that the road is infinite, right? It's going forever in both directions. And the answer is no. There's no possible way. There's no physical way, again, without, cheating, like I just said. There's no way for you to get from where you are on one side of the road to the other side of the road without crossing the road. So what does that mean in math terms? Well, let's examine this definition. So we're saying, okay, there's some function f, right? Again, some function f. And we're saying that there's two numbers. So we have two inputs, a and b. Remember that when we plug things into a function, it's going to be in the form of f of a and f of b, where f is your function, a is your input, and you're going to get some sort of output, right? You're going to get something and something. Okay. So we've already broken down the beginning of this. And the important thing is just when it says, let A be less than B, basically they're just saying that one number is not equal to the other one, right? It doesn't matter what two numbers you pick. They're just saying, hey, they can't be the same number. And by trichotomy, going way, 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 way back to like one of the first lectures we did, trichotomy just says, oh yeah, if they're not equal, then one is greater than the other, right? So they're just saying, okay, there's two distinct points. And we're going to plug those points into our function. And when we do that, we get two different outputs, right? Let's call this output 1. So I'm just going to say, we'll call this n, and we'll call this m. Okay, so the output of f of a gives us n, and when we plug b into f, we get m out, right? So we get two different numbers. Now, the important part here is opposite signs. So if we plug in f of a and say n is negative, so I'm just going to replace n with a negative sign, okay? Say we get a negative sign when we plug a in, and say we get a positive sign when we plug b in. Well, if that happens, then we're saying there's going to be some input. We don't know necessarily what it is, but there's going to be some input, which in this definition they call it c, such that c is going to be between your interval of a and b. And when you plug c into your function, you're going to get 0 back. And what does that mean if you're getting 0 back for your output? Well, again, we read this, we can always go to an ordered pair, right? So we can read this as c comma 0, and if you have a y component of 0, that's saying that this is an x-intercept. So what this is really telling you is that if you plug two numbers into your function, and the outputs are of different signs, so one is negative, one is positive, or maybe it's the other way around, right? Maybe the first one you plug in is positive, and the second one you plug in gives you a negative output, then at some point you had to have crossed the x-axis. So to give you a graphical representation of this, let's say you have some function, and I'm just gonna, draw a function, right? So, all right, it's doing some stuff, I have no idea what, right? There is no possible way that the output, so notice how all of the outputs so far are negative, right? When we define output, we're talking about the y values, right? So all of the y values so far are negative. There is no possible way for you to get a positive output or a positive y value without crossing the x-axis somewhere. Eventually you have to cross that road, right? If you're trying to get to that pizza place, eventually you have to cross the road. There's, it doesn't matter where you cross the road, but eventually it has to happen. So there's no way that you can go from a negative value to a positive value without hitting 0 on the y-axis, without your output being 0. And again, what that tells you is that there's no way for you to go from negative to positive without you having an x-intercept. So again, I know that still seems like a lot of talking, and maybe you still don't get it. Let's do an example, and I promise you it'll be way, simpler than the definition makes it out to be. Okay? So let's look at our example. Let's say we have f of x is equal to 2x cubed minus 3x minus 6. Okay? Again, this is a cubic function. I don't expect you to be able to solve this, just with the tools that we currently have. However, what I can do with the intermediate value theorem is I can show for fact that this function has a real solution between the intervals of 1 and 2. Okay, so this is given to you. Okay, whenever somebody says use the intermediate value theorem to prove that there's a solution between an interval, well, the interval is always going to be given to you. So in this case, I'm giving you the interval 1 and 2, and I'm telling you to use the intermediate value theorem to show that there is a real solution. So in this case, by our definition, we have an A and we have a B, right? In this case, A is going to be 1, B is going to be 2. So what this tells you is that we have to plug A and B into our function, right? F of A, F of B, and if the outputs are of different signs, so if one of them is positive and one of them is negative, then we have shown by the intermediate value theorem that at some point in this interval, somewhere between 1 and 2, there is in fact going to be a solution to our function f. Okay, so all we have to do is okay, well, what's f of 1? F of 1, well, that just means 1 is your input. So wherever there's an x, you plug in 1, right? So we say, okay, 2 times 1 cubed minus 3 times 1 minus 6. Okay, simplifying this, 1 cubed is still just 1, so 2 times 1 gives us 2, minus 3 minus 6. 2 minus 3 gives you a negative 1, minus 6 is equal to negative 7. So notice, and here's the important part, we started with a negative number for our first input. Okay, so for the first part of our interval, we got negative 7. Okay, so that what that tells us is that if the next thing that we plug in, which in this case is going to be 2, if when we plug in 2, we get another negative number back, then there is no solution in that interval. We have shown that it has not crossed the boundary. Okay. However, if we get a positive number back, then we have shown it has in fact crossed the x-axis. So let's go ahead and plug f of 2 in. So f of 2 means we're going to have 2 times 2 cubed minus 3 times 2 minus 6. 2 cubed is going to be 8, and 2 times 8 gives you 16, minus 6 minus 6. So minus 6 is minus 12. 16 minus 12 gives you positive 4. We got a positive number. Again, I don't care what that number is. The 4 is inconsequential. The 7 is inconsequential. What's important to me is this is a negative, this is a positive. So by IVT, or by the intermediate value theorem, we have shown there is in fact a solution in this interval. And you would just write, if this were on a quiz or on a test, you would just write exactly that sentence. By IVT, there is a solution in this interval, and you would write out the interval. There is a solution in the interval 1 to 2. Okay, so that is how you use IVT. That's it. All you're doing is you're given an interval, and you just test the boundaries of the interval. So you test 1, you test 2, and if the signs are opposite, you have a solution. If you don't know what the solution is, but you know a solution exists. If the signs are the same, you have not proven that a solution exists. Now, that's a stark difference from saying there is no solution. There could still be one, but by IVT, you haven't been able to prove it. Okay, so just keep that in mind. Okay, so let's see, how long have I been talking? I feel like I've been talking forever. 51 minutes. Okay, so why don't you guys go ahead and do your first classwork assignment. So what I want you to do is show that there is a solution in the following function. So the function is f of x is equal to x, oops, I don't know why I put the caret, x to the 5th minus 2x cubed minus 2. And this is on the interval of 0 to 2. Okay, so via IVT, just like we just did, prove that there is a solution. Show that there's a solution. Okay, so I'll give you guys a couple seconds. I'm going to get a drink of water while you guys do this, and let's see if you can figure this one out. All right, so let's go ahead and do this together. We want to show that there is a solution. So showing a solution just means we're taking the boundaries of our function of our interval, which is from 0 to 2, and we're going to plug those in. And if the signs flip, cool, we showed that there's a solution. So we take f of 0 and we plug in 0 wherever there's an x. So 0 to the 5th minus 2 times 0 cubed minus 2. Okay, so the first 0 to the 5th is just going to drop out. The second term is also going to drop out because it's negative 2 times 0. So we're just left with that negative 2 at the end. So f of 0 is equal to negative 2. And now we plug in f of 2. So f of 2, and by plugging in 2 into the following, if you guys needed it, totally okay, I understand. But 2 to the 5th should give you 32. So we get 32. Before I simplify, let me actually just write it all out. So 2 to the 5th minus 2 times 2 to the 3rd minus 2. 2 to the 5th gives you positive 32 minus 2 times 2 cubed. 2 cubed we know is 8, and negative 2 times 8 should give you negative 16 minus 2. And yeah, even on inspection, you already know this is going to be positive, but if you don't see it immediately, that's okay. 32 minus 16 is still 16. Minus 2 gives you 14. And once again, notice you had a negative for your first value. You have a positive for your second value. So by intermediate value theorem, you have in fact shown that on the interval from 0 to 2, there is a solution to f of x. You have shown that there is a solution exists somewhere in there for this function. Okay. So one topic that we've talked about at least a little bit, we've definitely defined it. We just haven't, I didn't make it a big part of the lecture before, is multiplicity. Again, if you don't remember what multiplicity is, that's okay. Multiplicity is the number of times a particular solution of a function repeats itself. So let's go ahead and look at just a quick example. If we have f of x is equal to x minus 3 squared, well, when you solve for x, when you're trying to find your x-intercepts, which is the same thing as trying to find the solutions, you know that well, you're just going to have x minus 3 twice, right? X minus 3 is equal to 0, x minus 3 is equal to 0, and when you solve, you get x is equal to 3 twice. You get it on both sides. So what we say here is that although there is only one solution, it occurred twice. So we say that x is equal to 3 has a multiplicity of 2. Okay, so multiplicity, again, is just the number of times that a solution repeats. And then coupled with that, there's another definition, which, it's good to know. A distinct zero is a zero in which we do not include a repetition, if any. So basically, if you had, and we'll look at a quick example, if you had 3 different solutions for your function and one of them repeated, well, even though you had 4 solutions total with, because you're including the one that repeated, you only had 3 distinct solutions because you're not including that repetition. So to show you what I mean, if we had f of x is equal to x minus 2 times x plus 2 squared, well, what this tells you is that when you're solving for x and when you're solving for each solution, you would set each one equal to 0. So you have x minus 2 is equal to 0, x plus 2 is equal to 0, and then again, x plus 2 is equal to 0, right? And when you solve, you get x is equal to 2, x is equal to negative 2, x is equal to negative 2. So notice that we have 3 solutions, but we only have 2 distinct solutions. And what I mean by that is we have a 2, we have a negative 2, but because negative 2 repeats again, we see that negative 2 has a multiplicity of 2, so we really only have 2 distinct zeros. Distinct is just another word for unique, okay? So basically, do we have how many different numbers do we have? We have 1 number, 2 numbers, but oh wait, negative 2 is repeated, so we don't count that again. So we have 2 distinct solutions. Turning points. I know I'm kind of like running through a bunch of things that don't seem like they relate, but they're about to relate very, very soon. So, turning points. The turning point of a function is going to indicate the local minimum or maximum of a graph. And when we're talking about local minimum, the word local means that it's not going to be the highest point or the lowest point of the graph in total. It's just that, maybe there was a bump in the graph, or like you could think about it like a hill, right? And in that hill, it was the highest or the lowest point of that bump. So what I mean by that is, say you have a function that kind of looks bumpy, like, something like this, right? So cool. This could be a polynomial function, right? And in fact, we've already learned that by the polynomial end behavior. Notice how these 2 points both go upwards towards infinity. So I don't know what polynomial this is, but I can tell you that the exponent is even, and I can tell you that the coefficient is positive, right? It's pointing upwards, it's opening upwards, just like a positive parabola. So I can tell you that, this has an even exponent. But in any event, what I mean by local minimum or local maximum is this point right here isn't the highest point that the graph ever achieves, but it's the highest point of that bump, right? We see that it kind of went up and then it goes back down. So when we talk about a function increasing or decreasing, we generally start talking about local minimums and local maximums. And we see that there's actually 3 of them here, right? There's one that there's 2 local minimums and 1 local maximum. There's 2 lower bumps where it kind of like bottomed out and then it started increasing. And then there's, a local maximum up here where, okay, it got higher than, other parts of the graph, but then it started decreasing again. Okay, so here's something that you should remember as far as turning points are concerned. So if f of x is a polynomial, okay, so again, this is only true for polynomials, but if your function is a polynomial of highest degree n, so of highest degree n, and degree is always talking about your exponent, then it has at most, and I'm going to underline here at most because not guaranteed, but this is the most it could have. It has at most n minus 1 turning points. Okay, And again, a turning point is telling you the point at which it either stops increasing and starts decreasing, or vice versa, right? It stops decreasing and starts increasing. So one or the other, but point is that your polynomial can only have n minus 1 turning points. So when we look at a function, like I always go to our handy dandy trusty parabola, right? So our trusty parabola looks like this. Well, notice there's only the one turning point, right? It bottoms out at one specific point. It was increasing here, and then it was decreasing there, and then it starts increasing on the right-hand side. So we see that there was the turning point where it stopped decreasing and started increasing. Well, you know that a parabola can only have at most one turning point, because you subtract one off of whatever your highest degree is. So for a parabola, the highest degree is just going to be squared, so a 2. So 2 minus 1 is 1. So a parabola can only have at most one turning point. When we're talking about x cubed, or a cubic function can have at most 2 turning points. And just to show you what I mean by that, a cubic function can look something like this, if there's other factors involved, of course, but it can look something like this. Now, this shouldn't be too absurd, right? Again, we talked about end behavior, and this, again, is a good idea of what x cubed will look like. It's just not centered at 0, which means that, okay, x cubed, something is being added to it or subtracted from it. But in any event, notice how we have one turning point here and then another turning point here. So for x cubed, well, x cubed has a max number of turning points of 2, one less than the exponent. Okay, and to really hammer down this nail, find how many turning points are in the function f of x is equal to negative x to the 4th plus 3x squared minus 2. Again, we're only concerning ourselves with the highest power. So the 3x squared minus 2, this piece does not matter in regards to turning points. The only thing that matters is our highest power, which is 4. So n minus 1 is equal to 4 minus 1, which is 3 turning points maximum, right? You can't have more than this, and it's not guaranteed that you can have 3, but 3 is the most that it can have. Okay, so what I want to do is I want to detail how you sketch a polynomial function. We're going to be putting together a lot of ideas, some from the past and some from what we just talked about today. So there is a 5-step process that you should take advantage of when you're trying to sketch a polynomial function. And this applies to quite literally any polynomial function at all. Okay, so your first step is you're going to determine the end behavior based upon the leading term. Okay, so end behavior, you're going to figure out the end behavior. Your second step is you're going to find all real solutions. Why are you going to find all real solutions? Well, finding all real solutions is the same thing as saying find the x-intercepts. So you're going to try to find all possible x-intercepts. Your third step involves test points. Yes, you can never escape test points. I'm sorry, they never go away. So your third is you're going to determine if your function is decreasing or increasing between the zeros, or between your x-intercepts, using test points. So use test points to determine, and I'm going to abbreviate this, increasing or decreasing. Your fourth step is you're going to find the y-intercept. So again, you found the x-intercepts in step 2, and in step 4, you're going to find the y-intercept. So you can kind of just, if you wanted to, abridge it to find all the intercepts, but I feel like it's good to go in order here. And then last but not least, sketch using the information above. Okay, so all the top 4 points are going to give you good information on how we do things. Okay, so what I want you guys to do is, for your second classwork assignment, I want you guys to try to follow these 5 points and sketch the second classwork assignment. Okay, so the second one is f of x is equal to x cubed minus 3x squared, minus 3x squared minus 4x. So try to figure this out just based off of the steps above, and we'll do it together in just a second. Okay, so go in order, right? To go in order means, starting from step one. So end behavior. What is my end behavior going to be? Well, luckily for us, the end behavior of x cubed is just x cubed. So we know, just without even guessing, we know that we're going to have a piece that goes upwards on the right-hand side, and we're going to have a piece that goes downwards on the left-hand side. And that's all there is to it, right? That's just one of the things that we had to memorize as far as end behavior is concerned. We know that if it's odd and if it's positive, which in this case, it's a cube, so yes, it's odd, and yes, the coefficient is positive because it's just a 1, we know we're going to get end behavior like this. Okay, so that's the first step, and great, first step's already done. And you don't even need to really do anything as long as you understand what it's going to look like at the end. Okay, so your second step is you want to find all of the real zeros. And again, what that means is you're trying to find all of the x-intercepts. And how do you find an x-intercept? Well, you're setting y to be 0, and f of x is the same thing as y. So 0 is equal to x cubed minus 3x squared minus 4x. Well, we have a cube. We haven't really talked about how to factor cubes all that much, but we did talk about how to factor in general, and we see that we have an x in every single one of these pieces. So what I want to do is I'm going to factor out an x. So I have x times x squared minus 3x minus 4. Oh, well, this is way more friendly, right? This is a quadratic. We can factor a quadratic. So we have that x on the outside, and x squared minus 3x minus 4. Hopefully you guys can all do this. I'm not going to spend too much time on this. If you need help factoring quadratics, please come talk to me privately at this point. So now we're going to have x minus 4 times x plus 1, right? Negative 4 times positive 1 gives you negative 4. Negative 4 plus 1 is negative 3. So hooray, right? And we end up with 3 factors. 1, 2, 3. And should that make sense? Yes, right? We have a maximum number of factors matching the highest exponent of our polynomial. Our highest power of our polynomial is 3, so it should make sense that we should get at a maximum 3 factors. So sure, we have x, x minus 4, and x plus 1. And what do? You set them all equal to 0. So x is equal to 0, x minus 4 is equal to 0, x plus 1 is equal to 0. Well, the first one on the left is already done. X is equal to 0. Yeah, that's done. You're just saying x is 0. Cool. Next one, x is equal to 4. And lastly, x is equal to negative 1. So great. We found our 3 x-intercepts, right? And if you want to write them in ordered pairs, this is the same thing as 0, 0, 4, 0, and negative 1, 0, right? These are ordered pairs, and you know the y component's always going to be 0 by the definition of x-intercept. So great. We have our 3 ordered pairs. Okay, so now what we have to do is we have to determine if f is increasing or decreasing between the zeros. Ooh, what does this mean? Okay, so increasing and decreasing. That means it should be negative or positive, right? We know, and we talked about test points before, and that's why we always try to, care about if things are negative or positive. So let's first plot things on just a number line. Obviously, when we graph this, we're going to want to, put this in 2-dimensional points, but just, for right now, let's just deal with just the number line. So our points are 0, negative 1, and 4. So what this tells us is, okay, we need to test 4 different intervals. We need to test this interval, this one, and this one. So we need test points for all 4 of these. So I'm going to pick negative 2, I'm going to pick 1, 5, and there's really no better thing than negative 1/2. You feel free if you want to use a more complicated fraction, but I'm going to stick with negative 1/2 here. Okay, so how do we test these? Again, we test them the same way that we always test fractions. So the way that, test points. And the way that we do it is we take our test points and plug them in. So we are going to plug in, and I'm going to plug it into my factored part here, which is the x times x minus 4 times the x plus 1. So I'm going to write that again, x minus 4, x plus 1. And we're going to start testing -2. So that means I'm going to have -2 times -2 minus 4 times -2 plus 1. Well, I know I'm going to have the -2 is a negative on the outside, times another negative, -2 minus 4 is negative, and then times a third negative, right? -2 plus 1. So that gives me 3 negatives all multiplied against each other. And they cancel in pairs, so I'm going to have 1 left over, so I get a negative value. What does a negative value tell me when I'm talking about, when I'm talking about increasing or decreasing? Well, a negative value is going to tell me quite a bit. And we'll talk about that in just a second, but it's actually going to tell you that it's decreasing. So over that interval, it's going downwards. So, okay, good to know. We'll keep that in the back of our heads for when we're sketching this graph. Okay, so next we have to do -1/2, unfortunately. We have to just bite the bullet and do this. So -1/2, that means I'm going to have -1/2 on the outside, then a -1/2 minus 4, and -1/2 plus 1. Well, the good news is we don't actually care about specific values, so as long as you can just kind of figure out what the sign is in your head, you're okay. So we know we're going to have a negative on the outside. We know that we're going to have negative minus a negative, so that's going to be another negative. But -1/2 plus 1 gives us a positive value. So 2 negatives cancel out times a positive. That gives us a positive. And a positive is indicative of increasing. So we can start writing these increasing, decreasing for the negative value. Okay. And continuing along, we have to test 1. So testing 1 here, that means we're going to have a 1 on the outside, 1 minus 4, and 1 plus 1. Okay, that's going to give us a positive on the outside, a negative on the inside, and a positive on the third. So that means that we're going to have a negative, right? Positives times a negative is always going to give you a negative. So we see it's decreasing once again. And over the last piece, which is 5, so 5, testing this, we have 5 minus 4, 5 plus 1, and we see that all of these are in fact going to be positive. So positive, 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 and all positives multiplied give you a positive, and so this is increasing. Okay, keep this here. I know it might not make a whole lot of sense just yet, but keep it here. We'll come back to this in just a second when we try to sketch this. And what's the last thing that we have to do before we can try to sketch? Well, going back, the last thing we have to do is just find the y-intercept. So, okay, that's fine. So finding the y-intercept, that's just set every x equal to 0. So, okay, finding the y-intercept just means y is equal to 0 cubed minus, oh god, I already lost track, minus 3 0 squared, and then minus 4 times 0. Well, everything is being multiplied by 0 because there was an x in every single term. So yeah, y is equal to 0, and this tells you that your y-intercept is at 0, 0. And you actually kind of knew this already, and the reason that you knew this already is because of this piece right here. We already found the point 0, 0, and because you know this is a function, and because you know you can only have an input mapping to one output, because 0 maps to 0, you knew there was no other possibility of another input also mapping to 0. So yes, your y-intercept is of course 0, 0, and you found that in 2 different places, but that's okay. Sometimes that just happens. So okay, this didn't give you any new points, but at the very least you found the y-intercept. So now let's go ahead and try to graph this. Let's try to figure out what the sketch is going to look like. So let's put our sketch right over here. Okay. So we know that our y-intercept and one of our x-intercepts is right at the origin. It's at 0, 0. So we can start with just putting that first point right there. What are our other x-intercepts? Well, our other x-intercepts are 4, 0 and -1, 0. So if this is -1, we'll plot that right there. And we'll say way over here, this is 4. So we'll plot that over here. Okay, so now we have -1. I'm also going to put the 0 here just so we all know this is the origin. So -1, 0, and 4. Great, those are our 3 intercepts. Now, the next thing that you should know is that the end behavior, right? We know the end behavior, and we figured that out before, right? The end behavior is going to look like this. So that means from the last point on both sides, that it's going to be the one on the right is going up towards infinity and the one on the left is going downwards towards negative infinity. So we know that this piece is just going to be going up that way, and this piece is just going to be going down that way. So we just need to figure out what's going on in the middle, but we actually already have the tools to do that because of the test points. We have the decreasing, the increasing, the decreasing, and the increasing. And how does this relate? Well, again, check our number line, right? We found that it was decreasing to the left of -1. And we also found it was increasing to the right of 4, right? So with our test point 5, we found that it was increasing. With our test point -2, we found that it was decreasing. This should make sense already because look at what's happening with our end behavior. To the left of -1, it's decreasing. And our test point proves that. Our test point shows, oh yeah, our end behavior makes sense. And to the right of 4, it's increasing. So yes, our end behaviors are already fact-checking us, and yeah, it's making sense. So now we just need to use the stuff in the middle. And okay, so the interval, we use -0.5. And what was that -0.5 for? It was the interval between -1 and 0. And we say that that was increasing, right? So we say, okay, well, it was going up like this, right? But eventually it has to come back down. So if it comes back down, okay, well, we know it's going to come back down and go through the point. That's the whole idea, right? It goes up, but it has to come back down at some point to go through the point. Now, I will make this note. For our class, and with the tools that we learn in this class, there is no way to know how high this is actually going to go. So it could go way, well, sorry, I don't want to go beyond 0. It can go way up and then come back down. And we have no way to show what's actually going on. We don't know how to show where the turning point is actually happening. We just know that a turning point does happen. Okay, so just take that with a grain of salt here. Unfortunately, we are constrained by the tools that we have, but we do know that a turning point is happening. So as long as you just show me that, there's going to be some bump, that's totally acceptable. It doesn't have to be super high. Just show me that it's happening. Okay, so now we see, great, it was increasing, but it has to come back down into the next point, which is through the origin. And from the origin, we see that it's decreasing, right? And again, we show this by our test point 1. To the right of 0, it's decreasing. So it goes down this way through 0, but it has to come back up at some point, and it comes back up through the point x is equal to 4, or our intercept. And now we have sketched this function. So our function that we started with, coming way back up here, f of x is equal to x cubed minus 3x squared minus 4x. We actually were able to make a rough sketch. And if you plug this into your calculator, a graphing calculator, or if you plug this online into some sort of graphing tool, this will actually give you a pretty similar sketch to what we have here, or to what you have on your paper. And the only difference is the bump here may be higher or lower, same with this bump here. Because again, with the tools that we have, we can't really show where the bump is happening. We just know that it's occurring somewhere between -1 and 0, and again, somewhere between 0 and 4. And does this make sense? Does this look like something that should make sense? Well, yeah, how many turning points can we expect to have with x cubed? What is the most amount of turning points that we can have with a function where our highest power is x cubed? Again, the number of turning points you can have is 1 less than your exponent. So we see that then the most number of turning points we can have is 3 minus 1, which is 2. And how many turning points do we actually have? Going back to our sketch. Well, we have 1 at each of our arrows, right? 1 at, and you know what, let me put them in blue here. So we have 1 here, and we have 1 here, right? Things were, for the one on the left, things were increasing, and then they started decreasing back towards 0. And then from 0, they were decreasing, and then at some point, it had to start increasing again to go back upwards through 4. So the entire idea here is that, yeah, our turning points make sense. Our increasing and decreasing makes sense according to our test points. Our end behavior makes sense because, again, we know that it should follow x cubed. Well, in this case, it actually was x cubed, but even if it wasn't, if it was like x to the 5th, we know our end behavior would model x cubed. And again, end behavior is referring to the legs that go on towards infinity. And yeah, so we were able to find the intercepts as well, which helped us plot this graph or helped us sketch it. So that's all there is to it. Again, it's really just a 5-step system. You figure out the end behavior, you find the x-intercepts, you use your test points to figure out if it's increasing or decreasing from those points that you found, from the x-intercepts. You find the y-intercept, and then you sketch it. You sketch it all. You just plug in your points onto your graph, and using your end behavior and using where, according to your test points, it's increasing and decreasing, you can figure out a pretty good estimate for the sketch of a graph. Okay, guys, I know I talked for a lot. I know that I definitely ran over at this point. Oh, man, I definitely ran over. I'm so sorry. So, yeah, we're going to definitely end the video here. Go ahead and try your hand at the homework. It's not going to be too much homework. I didn't load up because I know that you guys, have your test corrections and whatnot. So just try to do it and prepare yourself for the quiz on Friday, okay? So, everybody, have a great night or morning whenever you're watching this, and I will talk to you next time. Feel free to email me if you need any help. See you later.